everyone, welcome back. We're going to be covering now Predicates, Chapter 6 of Common Lisp Language. So a predicate is a function that tests for some condition involving its arguments and returns either true or false, meaning nil if it's false or some non-nil value if the condition is true. Right? So conditional control structures are cond, if, when, unless. Right? They basically use them to determine the situation, and if it's true, do this, so forth. Right? Predicates usually end with the letter P. A hyphen is placed before the final P if and only if there is a hyphen in the existing name. So if you want to say standard char, then you do standard char P, right? You're not going to put it all as one word. You do standard char P, separate them out. All right, and that gives maintains the spacing. The words give it still meaning. Let's see here. Okay, so again, as we've mentioned many times, nil is always nil. It can also be written as the empty list. T is always T, but in generally speaking, when we want to return a true value, any value is true, right? And if it's not nil. Okay. Let's see, general type predicates. Okay, so these are various predicates that are used to determine the type of an object, right? So if you say is this object type whatever it is, I want to say is it a number, is it a string, etc. Subtype is basically you want to ask if these two different types is one a subtype of the other, right? So it's true if type 1 is definitely a subtype of type 2, right? And there's actually a second return value to give you how certain the result is. So true would mean, yeah, this is 100% the subtype. And everything else, of course, is we're not 100% sure, but it could be, or no way. Okay, let's see here. Okay, null, and actually you'll see afterwards nil in a function position to basically say whether or not an object is true or false, right? So if it is null is true, if its argument is, of course, the empty list or nil, then it comes back as being true, right? Symbol P says whether or not something is in fact a symbol. All right, atom, yes, it is an atom. Now, true if its argument is not a con. So anything which is a cons or list is basically going to come back as false when you ask if something is an atom. And when you say cons P basically returns true, right? He says an empty list, though, is not a con, so that's a difference. So list P will return true even for an empty list, right? He says, but cons P will not. So it has to have basically be a cons, but not an empty list, okay? So let's see here. Number P, is this a type of number, any type of number, integer, which of course, if you use subtype, you'd be able to go back and forth and say, hey, integer is a subtype of number, right? But I guess the point is integer P, it says rational P, float P, real P, right? It says complex P, character P, right? All these again, just is it this type, is it that type? String P, is it a string? A bit vector, is it a bit vector, a vector? Remember the simple versions of vector, string, bit vector. Remember, simple basically says that this does, this does no ability, for example, to expand its size. It generally means to say, and not necessarily, but generally means to say that these are laid out very simply in memory. Array P, basically, again, is just an array, right? It's a package is the particular object the package designated, right? Function P, is this a function, right? Function P is in fact always false, right, for symbols and lists, right? So just keep that in mind. Basically, the function P, of course, if in fact it is a function, returns true. Right? Compile function. So, for example, on SPSL, everything is a compile function, so return true. But generally speaking, on those implementations that have interpreted versus compiled, that can be used to determine what the state of that particular function is in terms of its memory. Let's see also standard, standard char, string P, random. Again, all these again various different types we talked about early on. There are predicates for each one of those. Okay, some additional predicates. So these are important. There are many ways to express equality in Common Lisp. EQ, essentially two things if they have the same, if and only if the address is the same identical memory location, right? So two symbols, okay, if it's the same symbol both times, they're equal, right? They're EQ, right? He says the value of a function's address, if it's two different, if that's what the variable of those two different symbols representing variables, if they contain, both of them contain the same function, the exact same function, in the same memory location, that's true. So for example, two strings, they have different memory locations. So therefore, even though they are equal, right, they are not EQ. So keep that in mind. All right. So EQ basically is used mainly for symbols. You can't use it for numbers either. It's used for symbols. Now EQL, which is our next one, is just like EQ, but again, it also can differentiation between between numbers. So it's just like EQ, but if they are numbers, right, of the same type with the same value. So 1.0 is not the same as 1 without .o, right? The point is, character objects that represent the same character would also end up being true. Again, the reason, by the way, for having these, there are various different reasons, but one of the key reasons is efficiency. So when you're comparing EQ of symbols, it's very, very quick. EQL also very, very quick. So again, as you get into something like equal, right? Again, if you don't know, use equal. Very simple. But in fact, maybe in the beginning you might even start out with equal, but eventually you'll understand that if you're just comparing symbols, use EQ. You're comparing symbols and numbers, use EQL. So equal X, Y. So rough rule of thumb is that two objects are equal if and only if their printed representation are the same, right? So numbers and characters are compared as for EQL. Symbols are compared as for EQ. So equal, 1.0 and 1 are not the same still, right? So EQL does not. If 1.0 and 1, they essentially, if they printed them out on a console, they would be two different numbers. Therefore, they're not equal, right? Cons. So equal, right, is defined recursively for a few things, only a few things. One of those is, again, is when you're taking two cons and you're going to compare them to each other. The two cons cars and CDRs have to be the same. Arrays, right, is as if they're EQ with one exception. Strings and bit vectors are compared element by element. So arrays, generally speaking, they have the exact same array in memory, right? EQ, right? But strings and bit vectors have a special exception that they will actually look at the values themselves. So equal would actually mean look at this value, look at that value, meaning in terms of the strings value, and compare them. And the same thing when it comes to bit vectors. Upper and lower case letters in strings are considered by equal to be distinct. So uppercase T-E-S-T, it's not the same as test. Now equal P, by the way, does not make a difference between equal P, which we'll see in a moment, does not make a difference between Ks. Let's see here. So equal, EQAL, never recursively descends any structured data type other than the ones explicitly described above, which were conses, bit vectors, strings, and path names. Everything else, equal doesn't dip into it. It just compares, again, the memory location. It compares the number or character, again, just like EQL, meaning EQL. Meaning, again, it's looking at, in other words, if they're the same type and value. All right, now equal P is actually much more broad in definition. So what ends up happening is that equal P basically will compare components of a hash table, right, and see if the hash table values are all the same. It will also look at compare by number equality, meaning so 1.0 and 1 are both the same, right? It'll use char to be able to determine if two characters are equal. I mean, they may have, again, therefore it does not make a difference between upper and lower case. Equal P will also compare two structures, not classes and not objects, right? In other words, in the object system, but when talking about structures, though, it will go ahead and does this structure definition use the type option, right? If they use that, then that's all gone. But if they didn't use that particular option when using defstruct, then equal P is true only if the structures have the same type, the same defstruct, and they also have the same values in all their slots, right? So equal P has a little more functionality with that. If you're trying to find equal P, for objects, doesn't exist. You really would have to define your own equal equivalence function to be able to determine whether or not two things are equal. In other words, because only you would know basically how to compare, in other words, two objects. Okay, and or are also control structures. So they're and or and not are also Boolean values, right? Aces and but they also and or are also control structures because their arguments are evaluated conditionally. right? Not, of course, this doesn't apply. So not x. So again, it's actually the same as null we saw before. So not, sorry, before I say nil, it was not. Sorry, so not x will tell me basically if x is false, then this returns true, right? Again, just like null. And basically, like I said, so it goes one by one, at one after the next, right? Any one of them basically evaluates to a nil, right? It just then immediately returns without evaluating the remaining forms. So therefore, end this, this one's false, return right there and then. So you can actually have side effects going on through the various ands that will not be run. In other words, if the first one's evaluated, they won't be evaluated if the first and has already been evaluated. Okay. Or is the same way. Any form other than the last evaluates as something other than nil. So each one of them has to be nil. If something's not nil, it returns right at that point without evaluating the additional forms afterwards. All right, and that's number 6.